guys, in this video we're going to talk about the law of conservation of mass and how it applies to balancing chemical reactions. Our learning goals are to explain the law of conservation of mass and to be able to balance chemical equations when given the reactants and products. So the law of conservation of mass states that in a closed or isolated system, matter cannot be created or destroyed. And when I use the term system, I'm really just describing anything that we are talking about. Could be as small as a chemical reaction in a beaker, or anything as large as the universe, as long as it's isolated and we're not adding anything to it or taking anything away from it. And what this means for chemical reactions is that during a chemical reaction, matter is not created or destroyed. So we're not creating atoms and we're not destroying atoms, but rather what's really happening is the atoms that are present are rearranging themselves into new configurations that we see as new chemical substances. And how this applies to balancing chemical equations means that the atoms that we start with in a chemical reaction are going to be the same atoms that we end with in that chemical reaction. They're just going to be rearranged into those new configurations or new chemical products. So we're going to end up with the same number of atoms in our product side that we end up with in our reactant side. And when we balance or when we start off with a regular just unbalanced chemical equation, sometimes it looks like these equations defy the law of conservation of mass, because as they're written, when we rebalance the new products, those atoms are coming together in different ratios. And so without balancing this equation, it kind of looks like they don't follow the law of conservation of matter, or mass, but in reality, we just have to balance those and describe the quantities of those molecules that are going into and coming out of this chemical reaction. And we balance these equations using coefficients. And remember, those coefficients are those large numbers that we write at the beginning of a chemical formula to tell how many units or how many molecules we have. One thing that you want to be aware of is that you never ever want to change your subscripts when you're balancing a chemical equation. Those subscripts are part of each individually balanced chemical formula, and those subscripts are there to describe what it takes for that substance to be that particular substance. So we can't change those subscripts, because if we do that, we change the number of atoms that are involved in the making those chemical substances, and we don't want to do that to balance an equation. All right, so for example, let's go ahead and take a look at an example of a combustion reaction really quick. If we were to just write out the combustion reaction that's just basically showing what's happening, like just basic list of reactants and products, you can see that we've got methane and oxygen reacting to form carbon dioxide and water. And if I were to go through and count the atoms on either side, you would see that I've got one carbon atom here. I've got 4 hydrogens, 1, 2, 3, 4, and 2 oxygen atoms, right? Then on the other side, on the product side, if I were to go through and count these separately, I'd have 1 carbon atom, just 2 hydrogens though, and 3 oxygens. So it looks like we've got an imbalance here in the number of atoms. And that's not because there's anything wrong with our formulas or our equation, it just hasn't been balanced yet. And when we balance that, we use those coefficients. And so if you take a look over here at the balanced form, we've got a 2 here in front of that oxygen and a 2 here in front of water. And by adding those two coefficients to this equation, we've now balanced it so that we have the same number of each type of atom on both sides. So if we were to go through and recount these, I've got a carbon here, 1 carbon, 4 hydrogens, and 4 oxygens. Right? Then on the other side, I've got my 1 carbon. I've got 4 hydrogens, 1, 2, 3, 4, and 4 oxygens, 1, 2, 3, 4. All right, so all we did was double the amounts or the number of molecules for a couple of those substances, and it actually ended up helping us balance out this equation so that we can show what's happening to all of the atoms that go into this and come out of this. And really what we're doing when we're balancing these equations is we're showing the ratios that are required for this reaction to take place and form these products. All right, so I think the best way for me to explain this is to just go ahead and do several examples and just show you how to do this as we go. So the first thing I want to do is I'm going to list out all of the elements that are on both sides of this chemical reaction. So I've got nitrogen and hydrogen on this side, and then I've got nitrogen and hydrogen on this side, on the product side. And you need to have two lists because we're comparing the reactant side to the product side. And it's really helpful if your list of elements that are on both sides is in the same order for both of them, so that you can just compare right across from one another rather than bouncing around and trying to find those numbers. All right, so now the next step is to go ahead and just count all the atoms that I have on either side. So for nitrogen, I have 2 atoms on this side, and I have 2 atoms of hydrogen here. And on the product side, I've got 1 nitrogen and 3 hydrogens. So we can definitely see some imbalance. And now I'm going to go ahead and start balancing. And when you balance these equations, you want to start up at the top of your list. So in this case, we would start with nitrogen, and then you want to work your way down. And this is a pretty simple problem. So it's, there's not a lot of working our way down. We just have to go to do hydrogen next. But occasionally you'll have, several different things that you're trying to balance, and you'll start up at the top and you'll start balancing all the way down, and you get down near the bottom and you change something down there that ends up changing something that you balanced up above it. And if that's the case, you just want to go back up to that spot where the imbalance occurred and then work your way down that list again from that spot. So that helps you avoid bouncing around a lot and losing your place. It's very easy to lose your place and forget what the last number that you changed when you're balancing these equations. So let's just go ahead and start. So I'm going to start by balancing nitrogen. On the reactant side, I have 2 atoms of nitrogen. So I need to try to have 2 atoms of nitrogen on this side. And so what I'm going to do is I'm going to add a coefficient of 2 right here in front of that ammonia, NH3. And when I do that, it's going to change this number to a 2. But because nitrogen and hydrogen are in that compound together, it's also going to change the number of hydrogens I have. So that 2 is going to be multiplied by the subscript on H, and that's going to tell me that I've got 6 hydrogens now. All right, so nitrogen looks good. That's balanced. And now I'm going to move down to the next element, which is hydrogen. I want to balance hydrogen. And I've got 6 hydrogens over here on this side. I need to try to have 6 on this side. And so in order to get 6 hydrogens on this side, I can add a coefficient of 3 here. And 3 multiplied by 2 equals 6. And there we go. So this is our balanced equation. And what it's telling us is that for every molecule of nitrogen gas, it's going to take 3 molecules of hydrogen gas to produce 2 molecules of ammonia. All right, and this is going to be a really important concept later on when we start talking about stoichiometry. All right, let's do another example. This one's going to be a little bit different because the 2 of the compounds involved in this reaction contain a polyatomic ion, and that polyatomic ion is phosphate. So remember, you can identify which element or which compounds contain polyatomic ions by identifying the formulas that have more than 2 elements in them. So for example, this one has hydrogen, phosphorus, and oxygen in it. And because it has more than 2 elements, we can say that's got a polyatomic ion in it. And then if you need help identifying which one of those is a polyatomic ion, remember you can always refer to, wrong chart. You can always refer to your reference chart and take a look for those polyatomic ions. All right, so because the polyatomic ion in this compound also occurs on the product side, I can treat that as one unit. So I don't have to break it apart and count phosphorus and oxygen separate in this compound because this same polyatomic ion is on both sides of the reaction. That's the key here. It has to show up on the reactant side and the product side. All right, so when I go ahead and make my list now, I'm going to have hydrogen and the phosphate polyatomic ion and sodium and bromine. So make my list over here, hydrogen, phosphate, polyatomic ion, sodium, and bromine. Now I'm going to go ahead and do my initial count. So I've got 3 hydrogens. I've got 1 phosphate polyatomic ion. I've got 1 sodium and 1 bromine. And on this side, I've got 1 hydrogen, 1 phosphate polyatomic ion, 3 sodiums, and 1 bromine. All right, so now I'm going to start balancing. I'm going to start at the top. So hydrogen's at the top. I've got 3 over here. I need to try to have 3 on this side. So I'm going to put a coefficient of 3 in front of the compound on the product side that contains hydrogen. And that's going to change hydrogen to a 3, but it's also going to change bromine since they're in the same compound. So I'm going to change bromine to 3. And you want to make sure that if your coefficient that you add changes more than one of the elements, you want to go ahead and make those changes at the same time so that you're not forgetting to do it later and throwing off your balancing act here. All right, so now we've got hydrogen balanced. Now let's move down to the next thing. We're looking at this phosphate polyatomic ion, but it actually already looks like those are balanced. So I'm gonna say that's good. It makes it easy for us. So now let's go down and do sodium. I've got 3 sodiums on the product side. I need to have 3 on the reactant side. So if I go ahead and add a coefficient of 3 here in front of sodium bromide, then that's going to change my sodium to 3, and it's also going to change my bromine to 3, right? And that actually goes ahead and balances the whole thing for us. And so here is my complete balanced equation, right? All right, let's go ahead and do a combustion reaction. So combustion reactions, not always, but can sometimes have really large coefficients depending on the identity of the hydrocarbon involved. If there's a lot of carbons, you're definitely going to need a lot of oxygens to react with those. So let's go ahead and just list out our elements. I've got carbon, hydrogen, and oxygen on this side. Carbon, hydrogen, and oxygen. All right, so I've got 6 carbons, 6 hydrogens, and 2 oxygens. And then I've got 1 carbon, 2 hydrogens, and 3 oxygens on this side. So I'm going to go ahead and start by balancing my carbon. I've got 6 over here, so I need to have 6 on this side, so I'm going to put my coefficient right here. And that 6 is going to change the number of carbons I have here to 6. And then it's also going to change the number of oxygens I have. So now I've got 12, I've got 13 because I don't want to forget about the oxygen that's in my water molecule there. And so now my carbon is balanced, and now I need to balance my hydrogen. So I'm going to need, I have got 6 over here. I need to make this a 6. And so if I put a 3 in front of that water, then that changes my hydrogen to 6. But it's also changing my oxygen count again. So if I've got 12 coming from carbon dioxide, and now I've got 3 coming from water, now I've got a total of 15 oxygens. And now hydrogen is balanced, but now we have to balance oxygen. And we've kind of run into a problem here because I've got an odd number of oxygens on this side. And the only way that I can balance this is to have an even number of oxygens on the reactant side because of this O2 molecule right here. So I could play around with the numbers for a little while and try to figure it out. Or what I could do, and I know that this might make some of you cringe, I could start over, right? I'm going to start over. But instead of just starting over from scratch, what I'm going to do is I'm going to double my hydrocarbon. So if you have an uneven number of oxygens and the only way you can balance it is with an even number on the other side, then what you need to do is you need to start over and you need to balance or double your hydrocarbon, which means just put a 2 in front of your hydrocarbon. And when you do that, you end up with 12, 12, 2. And this is my initial count here, right? So I need to balance my carbon first. So I'm going to put a 12 here in front of carbon. That's going to make that a 12. And it's also going to change the number of oxygens I have to 25. All right, so that's 24 from carbon dioxide and then 1 from water. Then what I need to do is I need to balance my hydrogens. So I've got 12 over here. I need to have 12 on this side. And if I need 12, then I'm going to put a 6 there in front of water. And remember, last time that was a 3 and that was an odd number. Now I'm putting a 6 there and it's an even number. So 6 times 2 is 12. All right, so now hydrogen's equal. And that also, though, changed the number of oxygens I have. So again, I've got 24 oxygens coming from carbon dioxide, and now I have 6 oxygens coming from water. and that changes this to 30 oxygens. All right, and now that's an even number, and now I can multiply this by something in order to get 30 on this side. So if I multiply this by 15, then I get 30 oxygens, and we're equal. So here's the balanced equation for that combustion reaction. All right, so now let's go ahead and do this last one. I have phosphorus, oxygen, and hydrogen. And phosphorus, oxygen, and hydrogen. So I've got 4, 11, and 2. And now I've got 1, 4, and 3. All right, so let's go ahead and balance this. We're going to start by balancing phosphorus. Remember, we're starting at the top and we're working our way down. So I've got 4 over here. I need 4 on this side. So if I put a 4 here, that's going to cross that out, and that's going to give me 4 phosphorus. But it's also going to change the number of hydrogens that I have. So 4 times 3 is 12. It's going to have 12 hydrogens, and the number of oxygens. So it's going to give me 16 oxygens. All right, so phosphorus is balanced. Now let's balance oxygen. I've got 16 oxygens over here, and I need to have 16 on this side. I have 11, and the good thing about this, though, even though this is an odd number, 10 of those oxygens are in one compound, and 1 of them is in another compound. So if I just added a coefficient here in front of water, then I could potentially have 16 oxygens on this side. So I'm going to go ahead. I need 6 more oxygens, and there's only 1 here. So if I multiply that by 6, then I get 16 oxygens. But that 6 also changes the number of hydrogens, when 6 times 2 is 12. And so that balances both oxygen and hydrogen. So here's the final balanced equation for this last example. All right. Thanks for watching Buffered Chemistry. Subscribe to my YouTube channel for more chemistry help.